So the grouping strategy says if you want to organize stuff and you want certain things grouped together, like certain people have to sit together, or we're going to have an example where we have certain kinds of things that need to stay together, but we still arrange things in an order with different groups. The number of ways you can do that is you first figure out how many groups do I have. So, and then you do the factorial of the number of groups that you have, and then arrangements of each group individually. Now this is easier to see if we use an example. So let's say we look at my collection of math books, and we're going to say that I have 4 calculus books. They're all different. 5 algebra books that are all different. We don't want to get confused with an identical objects question here. And 4 different geometry books on a shelf. And I want to put them on the shelf. I'm wondering how many ways can I arrange them on the shelf, but I want to keep the calculus books together because that seems to make sense. I want to keep the geometry and the algebra books together because that makes sense. Well, the way that we do that is my first decision that I need to make is how am I going to arrange my groups? Well, I have 3 groups, and if you had 3 things and you wanted to arrange them, does it make sense that you would have 3 factorial choices to do that? It could be algebra, geometry, calculus, geometry, calculus, algebra, geometry, calculus, geometry, algebra. Which one haven't I counted? Geometry, calculus, algebra, calculus.
Sure.
6 ways. So first I decide which group's going to be first, which group's going to be second, which group's going to be third. Then once I've decided that, let's say my calculus went first. How many ways could I arrange my calculus books? There's 4 of them. So there'd be 4 factorial ways that I could arrange those books. And then there's my algebra books. How many ways could I arrange my algebra books? There's 5 of them, so there'll be 5 factorial ways of arranging them. And then finally my geometry books. Multiply each of these decisions together, and you would get a total. So in a grouping strategy, what it said in the initial slide is first we figure out how many groups that we have and arrange the groups. Then we arrange within each group. And you can figure out the total that way. So this, like question 7 and 8 that you were asking before, this one's similar to that. You've got 5 people, Amy, Bill, Jill, Lee, and Tom. They're all sitting on a park bench. Normally, that would be 5 factorial ways that you could sit them all on the park bench. But it's springtime, and Jill and Bill want to sit together. Aww. So what do? We group them together. So we sort of glue Jill and Bill together. And we can either think of this as now there are 4 groups, because there's the Jill, Bill, there's Amy, Lee, and Tom. Or you can, sometimes people even think of this one as 4 people, because Jill and Bill are never seen apart from this moment on. Well, just wait. The story thickens later. But Jill, you ever see those couples that you never see them apart? You almost start thinking of them as one person. So we can almost think of the Jill, Bill as one person, and then there would be 4 people. And so our groups, there's 4 of them. Because only Jill and Bill have to sit together. The main mistake that people make in this one is thinking that Jill, Bill is one group and that the other 3 are another group. But you could have Jill and Bill sitting together in between those other people. And so the other people don't have to be their own group. So first of all, there's 4 factorial for the groups. Then when you look at the individual groups, one of the groups is Jill and Bill. And they could sit together holding left hand, right hand, or right hand, left hand. So there is 2 ways, or 2 factorial ways, that you could arrange them. For example, if Jill and Bill, there's your 5 spots. If Jill and Bill were on the end, right, it could be that way. Or it could be Bill, well, Bill first, and then Jill second, right? So that's why there's 2 factorial. Now for the other groups are, and you don't have to write this down, but if you did write them down, can you see that you can't arrange them any more ways because there's only 1 in that group. So this part multiplying by 1 wouldn't be necessary, but if you wanted to put it down, you could, because that's the grouping strategy. Say, how many groups do you have? We have 4. So it's 4 factorial ways for deciding. And then the only group that has more than 1 is Jill and Bill, because they could be Jill Bill or Bill Jill. And multiplying all this together, there's 48 ways that Jill and Bill could sit together. Now spring is really spreading, and in part B, the next week, now Jill and Bill are sitting together, and Lee and Amy also want to sit together. So you have your 5 people, Jill and Bill are together, Lee and Amy are together. So how many groups do we have now?
What's going to happen to Tom?
Oh, Tom gets his revenge in part C, don't worry. Poor Tom, though, in this week, all by himself. So there's 3 groups, so then you have 3 ways of arranging them, right? 3 factorial ways of arranging them. Then there's still the Jill-Bill group that can be arranged Jill-Bill or Bill-Jill. And now there's the Lee-Amy group that can be arranged Lee-Amy or Amy-Lee. And you wouldn't have to write Tom down because it's just multiplying by 1. And so figuring this out, there will be 24 ways. Poor Tom. Okay. Now, part C, and I'm just going to hide this for now, as that might be on your notes as well, but you can just watch. So now we're not worried about Lee and Amy. They could sit together, they couldn't sit together. They're kind of on again, off again. That's not a big deal. But something happened. I don't know what happened with Tom, but now Jill and Bill must not sit together.
Oh, restraining order.
Okay. I'm still surprised that they go to this bench every week and would sit down, but now they're deciding that they're going to sit down, but they are not going to sit down next to each other. So how do we do that? And as it says in your notes, this is a place where the not strategy comes in. Because if you try to count this directly, it's possible, but it's hard. It's hard to figure out, okay, so if I have my 5 spaces, and I put Jill here, then this is not Bill, right? And then, so if I put Jill here, there's one choice. And this has to be not Bill, so then there would be only 3 people that could sit there. And then 3 and 2 and 1, and that's one possibility if Jill sits on the end. But then Jill could sit in the second spot, so I have to think, okay, next to her is not Bill, next to her on this side's not Bill. And you could slowly count all those separate cases and get a total, but it's going to take a long time. So the strategy that is easier to use is the not strategy, and the not strategy comes into place when it's easier to count the bad things and subtract them from the total than it is to try to count the good things. In this case, the total is really easy, right? 5 people on a park bench, 120 ways. The bad ways, well, we just learned that with grouping. The bad ways are where Jill and Bill are together. We did that in part A. In part A with Jill and Bill together, we found out that there was 48 ways that they could sit together. So if there's 120 in total, and 48 ways where Jill and Bill are sitting together, if we subtract the bad from the total, there's 72 ways where Jill and Bill won't sit together. Does that make sense? So this is the grouping strategy. When things need to be put together, you can group them together, and often these strategies get put together. Like here we have the not strategy and the grouping strategy combined together, because it was easier to count how many ways Jill and Bill were together and subtract it from the total. Our last strategy is permutations with cases. Sometimes you can't count everything at once, and so you have to break it up into different cases and count each of those cases separately, and then you can add them up in the end. So this question, how many numbers of at most 3 different digits can be formed using the digits 0 through 9? So this is a cases question because I could have 3 digits, I could have 2 digits, or I could have just 1 digit. And I can't count those all at the same time because they're different sizes. So once you realize you can't count something all at the same time, you break it up into your different cases and you do a little description of what case 1 would be. So let's say we want to start with our 3-digit number. So you would draw your 3 spaces for your 3 digits. Do we have any restrictions on any of the spaces? Is this a 3-digit number? No, because that's 95. That's a 2-digit number. And so there is a restriction in that our first digit can't be 0. So how many choices do we have? We have 9 choices because we have to take 0 out. And then you can put 0 back in, and you have 9 choices again. And then finally, 8 choices in the end. So there's 648 ways using the digits 0 through 9 that are all different. So then we can go through case 2. 2-digit numbers. 2 spaces. Again, we have a restriction on our first digit. It can't be 0. So we have 9 choices for that. And for our second digit, we can't use the number that we used in our first one, but we can add 0 back in. So we would still have 9 choices for our second digit, which gives us 81. Yes?
How would we do the first problem, I mean, the one of the 3 digits, if they tell us that we can't put a 0 in the middle position?
So then there would be 2 restrictions. You know, well, you know that 0 is not in the first one, and then 9 by 8 by 8. And case 3, one-digit number. Are there any restrictions here? And then we can get into a debate. Is 0 a number? Yes. It's a number, and so we could say that there's 10 then. Add up all of our choices. We get 648 plus 91, 739 total. So this cases question was really easy to see because we were counting different sizes of things because it said at most 3 digits. Often our cases come up where it's a spaces question with restrictions, which was one of the first things that we did, our fundamental counting principle with restrictions, but the restrictions have an overlap in both of our restrictions. So example here, how many 3-digit numbers, only using 1, 2, 3, 4, 5, have to be greater than 300 and even. So if I tried to do this with one case, all at once, if it's greater than 300, can you see that my choices, there's a restriction on my first digit. The restriction is my first digit has to be a 3, a 4, or a 5. There's also a restriction on my last digit. Because it has to be even, it would have to end with a 2 or a 4. So when we try to do this directly, we deal with our restrictions first. If you said 3 choices here, why can't I just say 2 choices there? What? I might have chosen this 4. And if I chose that 4, then that 4 would not be a choice for my second restriction. So then I should put 1. But I don't know if I chose that 4. I might have chosen the 3, in which case I would have 2 choices for my last one. So when we have 2 conditions or 2 restrictions and those restrictions overlap, then we have to break it up into cases. And we break it up into cases so that our restrictions don't overlap. And often there's more than one way to do that. So here's one example. Right? My problem is that 4. So I need to decide how I'm going to break up those restrictions to deal with that 4. I could, well, here, I'll start with my favorite way of doing this one. Since this one only has 2 choices, I'm going to say, let me end with a 4. So I would have my 3 spaces, and I'm going to say that I'm ending with a 4, which gives me only 1 choice here. My first restriction now, how many choices do I have for this one?
2.
Right? It can only be the 3 or the 5. So again, we write underneath the space what our restriction is. That's going to help us not make a mistake in putting the right number of choices in. So I know that this one has only 2 choices. There's no restrictions left on here. How many numbers do I have left? 3 numbers left. Because we're not allowed to repeat anything, so there's 6 choices here. Have we counted all the numbers? No. What haven't we counted? Numbers that end with a 2, right? So we counted all the even numbers that ended with a 4. That was case 1. Now we're going to count all the even numbers that end with a 2. Still 3 spaces. We're going to say this is a 2, 1 choice there. How many choices do I have for the first one? Could be 3, 4, or 5. So there would be 3 choices there. You've used up 2 of your 5 numbers. 3 choices left. For 9, there'll be 9 numbers that end with a 2. Your total number, once you've counted all the cases, you can add up your cases that are separate. You notice that there's nothing that I counted in case 1 that overlaps in case 2. So when we're separating our cases, we're trying to count things separately so that in the end we can add them up to put them together. Can you see another way that you could have broken up the cases? Another way to still count everything. What would I, and you don't need to write this one down, but what could I'll just leave my spaces there. But how could I count this differently? And we'll see if we still get 15 in the end. So the first time I used my second restriction and broke up the 2 and the 4.
You could have done start with 4 and then not start with 4.
Start with 4. And then start with 3 or 5. 3 or 5. So if I started with a 4, there'd be 1 choice there. This has to be a 2 then, 1 choice there, and 3 numbers left, 3. And here, I have a 3 or a 5. And is it wrong if you decided to do 3 cases and start with 4, start with 3, start with 5? No. It would have worked out to be exactly the same, but this is a little bit quicker.
Would you have two?
I have 2 choices here, 2 or 4, and 3 in the middle. For 12, does it still add up to 15? Yes, it does. So what you do once you realize that there is an overlap with your restrictions and you have to use cases, the idea is choose one of your restrictions and break it up. I chose the last one because there's only 2 choices, which really meant that I was going to have 2 cases, end with the 4, end with the 2. You could have chosen the first one, as you see here, and we did it in 2 cases, but you could have also done the first restriction in 3 cases. And it's not wrong if you do a longer method. Break it up into your cases, count each case separately, and then add it up in the end. Part B, we need to be greater than 232. We're still using the numbers 1, 2, 3, 4, and 5. So in this one, can you see that your first number could be a 2, a 3, a 4, or a 5? That's the possibilities. But we have problems here because I don't know what I would put second if I chose the 2. Can you see that the 2 is going to cause problems?
Yeah.
So what I like to do in these ones where it's greater than, because that 2 is going to cause problems, is in my first case, I realize there's a problem in my first digit. So I'm going to start with numbers that don't cause a problem. If I start with 3, 4, or 5, can you see there's no problems after that? Because if I start with a 3 or 4 or 5, I've got my 300s, 400s, 500s. It doesn't matter what other digits I put in. I'm going to be guaranteed to be bigger than 232. So starting with a 3, a 4, or a 5 will guarantee that my number will be bigger than 232. So there's no restrictions left on the last 2 digits. How many choices do I have left? Because I've used up one of the 5 numbers. Now I've used up 2 of the 5 numbers. There'll be 36 numbers. Well, what haven't I counted? Starting with a 2. But then my next number could be a 3, a 4, or a 5, but the 3 is going to cause some problems. So again, the same idea. What would I have to do for my second digit to guarantee it's going to be larger? Well, then I would have to end with, then my second one would have to be a 4 or a 5, because that would count all the numbers in the 240s and the 250s, and they would guarantee to be bigger than 232. So I have my 3 spaces. I'm starting with a 2, counting numbers in the 200s, and then to guarantee that it's going to be larger, I go 4 or 5, because that will count numbers in the 240s and the 250s, and then it doesn't matter what the last digit is. I've used up 2 numbers. I have 3 numbers left, so there'll be 6 ways. What haven't I counted?
The 30 range.
My numbers in the 230s. So case 3, start with your 2, 1 choice, then a 3, 1 choice, and then in order to be larger than 232, how many choices do you have here? 2. Only 4 and 5. 3's already been used. But that's a common mistake, is putting 3 back in again. But this question said we're not allowed to repeat our numbers, So there's only two choices here. If we add up all of our totals, 36 plus 6 plus 2, we get 44 in total. So this is the end of our permutations note. If we would summarize all of our strategies to date, we have our spaces, which is the fundamental counting principle. Within our space, in our spaces, sometimes there's shortcuts, like you could use the NPR formula within spaces, but you could use spaces instead. We've also had with spaces that you have to sometimes we have restrictions. So you have to deal with your restrictions first. So we started off with the fundamental counting principle. We added restrictions to the fundamental counting principle. Another strategy that we came across was identical objects. These are our Mississippi questions, or the route questions where you're going north a certain number of times and east a certain number of times. So when you recognize that a question has identical objects, you're going to use the Mississippi strategy. After identical objects, we are introduced today to the grouping strategy. Sometimes you can't count things all at the same time, and you have to break it up into cases. We saw that in the question where we had the president and secretary selected, male and female, and then female and male. You had to count them separately and add them together. We often see cases questions with restriction questions where the restrictions overlap. You have to have the first digit needs to be a 4, the last digit could be a 4. We've got a problem there, so then we need to deal with it with cases. And a strategy that comes up within these ones that we'll put down as well is our not strategy. And that sometimes it's easier to count what should not happen and subtract it from the total. Like we saw when Jill and Bill cannot sit together. It was easier to count all of them and subtract the bad ones as our not strategy. So for the rest of class, you're going to be working on finishing up permutations 1 and 2, and if you're done those, working on permutations 3 and 4, and they're all mixed together. So all these strategies are mixed together, so you have to be able to read a question and then try to fit it into what would be the best strategy for me to use to solve this kind of question.